Hydraulic turbines are mainly Pelton wheel turbine, Francis turbine, and coupling turbine. Pelton wheel turbine is a pure impulse turbine. Francis turbine is impulse and reaction turbine, and coupling turbine is a pure reaction turbine. So today's discussion is for the Pelton wheel turbine. So let's begin the discussion about the Pelton wheel. This is working principle of Pelton wheel turbine. Pelton wheel turbine is a pure impulse turbine. That means reaction of this turbine is zero. The total energy is converted into the velocity energy is only in the nozzle, and there is no pressure drop at Pelton wheel bucket. That means inlet and outlet pressure of bucket is the same. Pelton wheel turbine is used for high head and relatively lower flow rate. Typically, the head is above 300 meters. You can see this is a schematic of Pelton wheel turbine, where this is you can nozzle, and this is the, we call it is a wheel or Pelton wheel, and a rod inside is a rotor. Buckets are attached to this rotor, and water is coming from the high head and high velocity of the nozzle, which is impulse, is striking the buckets, and because of this it rotates. So same thing, it is written here, the high head water comes from the reservoir to the nozzle of the turbine through pipe. The main function of nozzle is to convert high head fluid into the velocity. That means high pressure, you have to convert it into velocity in the nozzle. The high velocity of the fluid is coming out from the nozzle, which is coming here, extract the bucket of the Pelton wheel. This is the bucket. The buckets are fitted on the runner or shaft. This is shaft or runner, which is fitted on the buckets are fitted on the runner or shaft. Thus, a runner rotates due to the impulse section of water. The pressure at the inlet and outlet of the runner is the same. You can see both are same, inlet and outlet. And so no reaction occurs in the bucket. Typically, number of nozzles are limited to 2 in case of vertical runner and 6 in case of horizontal runner. Thus power is produced due to impulse action only. That is why Pelton wheel is a impulse turbine. The function of nozzle is also to control the flow of fluid for off design operation of the turbine. That means by movement of this sphere, flow is controlled. If you move towards this side, there is a minimum cross section area, so flow will be less. Moment it starts moving away from this, area increases and flow is increases. So this is how the flow is controlled through this nozzle using the sphere. So how flow is controlled? This is achieved by the movement of a sphere which changes the area of nozzle, and hence flow is controlled. The runner is enclosed in the casing. You can see this is a runner which is enclosed in the casing. And typical construction of Pelton wheel turbine is shown in the right side. And bucket, you see the water is coming centrally and it is deflected on both sides of the bucket. The Pelton wheel turbine bucket, this is runner with bucket. This is a schematic of the bucket. So you can have details of the buckets, like bucket length is A. This is bucket length, it is shown here. Then this is a B, which is bucket width. It is shown as a B, which is bucket width. Then bucket height is a C. This is bucket height, which is shown as a C. Then bucket depth is a D. You can see here, same is shown here. This is depth of the bucket. So this is bucket depth is a D. Then we have notch. So notch width is shown as a E. This is notch width, and notch depth is F, which is shown here. Here this is a notch depth, which is shown as F. So this is a detail of the bucket, which is shown in the A, B, C, D, E, and F in terminology. Now let us understand about the hydraulic efficiency of Pelton wheel turbine. Hydraulic efficiency is defined as the ratio of Euler head and hydraulic head. Euler head we know U2 into Cw2 minus U3 into Cw3 in joule per kg, which is Euler head or actual head, and hydraulic head, which is HS, is equal to G into H, which is also in joule per kg. So by definition, hydraulic efficiency is equal to U2Cw2 minus U3Cw3 bracket close upon HS, which is shown here HS. Now what are these terminology? U2 and U3 are inlet and outlet mean diameter tip velocity, and both are same. So U2 and U3 are same. CW2 and CW3 are inlet and outlet mean whirl or tangential velocity in meter per second. H is hydraulic head in meter. G is acceleration due to gravity, which is 9.81 meter per second square. C2 is a nozzle outlet velocity, and C0 is a spouting velocity, which is meter per second. So now a spouting velocity is equivalent to conversion of total ideal hydraulic head. So we can write a spouting velocity C0 is a square root of 2 into HS. HS is shown here. And inlet absolute velocity C2 is equal to CV into a square root of 2 into HS. That means C0 and C2 are same. That means a spouting velocity C0 is equal to inlet absolute velocity C2 if the CV or coefficient of nozzle velocity is considered 1. Typically, the CV is in the range of 0.98 to 0.99. So if you consider CV is 1, a spouting velocity is equal to inlet absolute velocity. So it has been seen that the hydraulic efficiency depends on U2, that is inlet outlet mean tip velocity, and hydraulic efficiency is a maximum when U2 is a half of nozzle outlet velocity C2 or a spouting velocity C0. That means if you see in the graph, it has shown on U2 upon C2, sorry, C0, and here shown U2 upon C2. On if you see it is a max, it is shown it is a maximum when U2 upon C0 is 0.5, that is half. Similarly, U2 upon C2 is also maximum when it is 0.50, that is half. So efficiency is a maximum. Hydraulic efficiency, y-axis is hydraulic efficiency, x-axis is U2 by C0, and here U2 by C2 on x-axis. So it is maximum when it is equal to half or 0.5. So hydraulic efficiency is the maximum when U2 by C0 is 0.5 or U2 by C2 is 0.5, because U2 C0 and U C0 is equal to U2 considering CV is equal to 1. Now the Pelton turbine power. Pelton turbine power is associated with mass flow rate, hydraulic head, and hydraulic efficiency. So turbine power is equal to mass flow rate into hydraulic head into hydraulic efficiency upon 3600 into 1000. So turbine power can further written, mass flow rate can be written like volumetric flow rate into density is equal to mass flow rate into hydraulic head into hydraulic efficiency divided by 3600 into 1000. So turbine power P is equal to Q into RD into HS into ES upon 3600 into 1000, where P is power in kilowatt, Q is volumetric flow rate in meter cube per hour, RD is the density of fluid in kg per meter cube, HS is hydraulic head in joule per kg, and ES is hydraulic efficiency, which is constant. So with this, thank you very much for watching this video.